Hello friends, I am Adeesh Deshpande from Fergusson College. We were discussing chapter number 7, that is elements of group 16, 17 and 18 elements. These are p block elements, out of which we completed the discussion of group 16 elements and group 17 elements. Today we are going to discuss group 18 elements. So students, just to revise, these group 16, 17 and 18 elements constitute P block of the periodic table. Of course, three other families also are the part of this P block. Today we are going to discuss group 18 elements. So this is the last group of the periodic table. Group 18 elements. So which elements are included in group 18? Elements included are helium, that is He, atomic number 2, neon, Ne, atomic number 10, then argon, Ar, atomic number 18, krypton, that is Kr, atomic number 36, xenon, Xe, atomic number 54, and radon, Rn, atomic number 86. So these elements constitute group 18 of the periodic table. These elements are all gases in nature, and these are called as noble gases. Noble gases means the elements never take part in chemical combination and hence called as noble gases. They exist in the form of gases only, chemically inert. So one more name, inert gases. So these elements, helium, neon, argon, krypton, xenon and radon, all these elements are gases. They are chemically inert. That means they do not take part in chemical combination and therefore called as noble gases or inert gases. Now amongst these elements, radon is radioactive in nature. Other gases occur in very small amounts in the atmosphere, and therefore one more name for these gases, that these gases are also called as rare gases. Rare gases. So three names: noble gases, inert gases and rare gases. Now to be precise, why these elements are noble gases? Because they are neither electropositive nor electronegative. So electropositive character is the character of the element or the atom of that element to donate electron and to form a cation. And electronegative character is atom of the element gains electrons and forms a negative ion, or they have ability to form covalent bonds. So this is electropositive and electronegative nature. Now these gases neither form cations by donating electrons, nor they form anions by gaining electrons, nor they form covalent bonds. So their inclusion of group 18 in between group 17, that is containing halogens, most electronegative, and group 1 containing alkali metals, most electropositive, is justified. So what is the actual position of these group 18 of the periodic table? They are present at the end of the periodic table. That is the last group. Just before this is group 17, which we studied, that is the group of halogens, these halogens are most electronegative elements, as we studied in the last class. That is, they readily form anions and they also possess ability to form covalent bonds. And if we consider the group of the elements after group 18, then after group 18 it is group 1, that is very beginning of the periodic table. This is the group of alkali metals. These metals are highly electropositive, that is, they readily donate electron and form a positive ion. So, if we just consider the position of group 18, then before group 18 is group 17, halogens, highly electronegative, and after group 18 is group 1, highly electropositive, that is alkali metals. And so the position is in between strong electronegative elements and strong electropositive elements. Electronegative elements on the left side, electropositive elements on the right side. In between these two, group 18 elements are situated. So these are noble gases, and thus the position of group 18 in the periodic table is justified. Now, what is the occurrence of these group 18 elements? Except radon, all noble gases occur in the atmosphere. So abundance in the dry air is approximately 1% by volume. That means all noble gases except radon, they occur in dry air and just 1% by volume as the composition. In that also argon is the major constituent. So remaining gases are present in very small amount. Commercial source of helium is natural gas. Natural gas is much rich with helium. So that is also considered as the commercial source of helium. Helium and neon are also found in the minerals of radioactive origin. So here are some of the minerals which are listed out: pitch blende, monazite, clavite. Now these are radioactive minerals which also contain helium and neon, these two gases. Radon is the decay product of radium 226. So radium is a radioactive element. It undergoes alpha decay and thereby it forms radon. Xenon and radon are the rarest elements of the group. So this point also one has to remember. Now what is the electronic configuration? Electronic configuration of helium is 1s2. Atomic number is 2. So in the first shell, 2 electrons are present, duplet is complete. All other noble gases have electronic configuration of the type ns2np6. So following is the table which gives you electronic configuration of all the elements. So helium atomic number 2 configuration is 1s2. Neon atomic number 10 configuration is helium core 2s2 2p6. Argon atomic number 18 electronic configuration is neon core 3s2 3p6. Krypton atomic number 36 configuration is argon core 3d10 4s2 4p6. Xenon atomic number 54 configuration is krypton core 4d10 5s2 5p6. And radon atomic number 86 configuration is xenon core 4f14 5d10 6s2 6p6. So if we consider outermost shell, then in neon it is the second shell. In argon it is the third shell. In krypton, fourth shell. Xenon, fifth shell. And radon, sixth shell. So from neon to radon, you will come to know that outermost shell contains 8 electrons. S orbital contains 2 electrons. P orbital contains 6 electrons. So in all these atoms, 8 electrons are present in the outermost shell. That means we can say that octet arrangement is complete in the outermost shell. Now we know that when octet is present in the outermost shell of any atom, then that atom is considered as stable. And so in general, if nth shell is the outermost shell, then we can write the configuration as ns2np6. Now the next point is atomic properties. The very first is atomic radii. Atomic radii increases down the group with increase in the atomic number and subsequent increase in the number of the quantum shells. This part is similar to those of the earlier groups. So as we move down the group, atomic number increases and electrons are added in the various quantum shells. At every time there is introduction of a new shell. So overall size of the atom increases and thus atomic radius increases as we move down the group, that is from helium to radon. The atomic radii of noble gases are larger than those of halogens due to increased electronic repulsions between completely filled valence shell. So this point one has to remember. If we consider a periodic trend across any period, then we studied that as we move from left to right in any period, size of the atom decreases. Now as noble gas element is always at the end of every period, according to the general trend, that noble gas element should possess the smallest ever atomic size. But this is not the case. Just preceding the noble gas, halogen which is present in that period has the smallest ever atomic size. And the noble gas has a little larger atomic size. So why this is so? The reason is mentioned due to the increased electronic repulsions between completely filled valence shell. So completely filled valence shell and thereby occurrence of electronic repulsions, as a result of which size of these noble gases at the end of every period is little bit higher than the preceding halogens. The next is ionization enthalpy. Due to the stable electronic configuration, these gases exhibit very high ionization enthalpy. So octet arrangement is complete in the outermost shell. So in s orbital and p orbital, they are filled to the capacity. In every orbital, s orbital and these p orbitals, electron pairs are present. And so it is very difficult to remove an electron and to form a gaseous cation. And so ionization enthalpies are very, very high. But as the general trend studied that ionization enthalpy decreases down the group with the increase in the atomic size. This holds good for noble gases also, because in noble gases, Size of the atom increases as we move down the group, and therefore ionization enthalpy decreases. Then the next property is electron gain enthalpy. Due to stable electronic configuration, these gases have no tendency to accept electrons, and therefore they have large positive values of electron gain enthalpy. No requirement of electron to complete the octet or like that. And so no tendency to accept electrons to form a negative ion. And so large positive values of electron gain enthalpy. Now physical properties. Physical state. All the elements of group 18 are colorless, odorless, tasteless, and monoatomic gases. So this point one has to remember, monoatomic gases. Then melting and boiling points. With increasing atomic size, polarizability of the atom increases and the magnitude of van der Waals forces increases down the group. Therefore, melting and boiling points increase regularly from helium to xenon. The next physical property is solubility in water. Noble gases are sparingly soluble in water. The solubility of inert gases increases on moving down the group, that is from helium to xenon. So this is a table that shows you actual values of some of the atomic and physical properties, that is atomic radius, ionization enthalpy, electron gain enthalpy, melting point, boiling point, etc. So it is exactly in accordance with what we have discussed just before this. Now chemical properties. The first is oxidation state. Basically, noble gases possess stable valence shell electronic configuration, that is Ns2Np6 with completely filled orbitals. And so they have no tendency to gain electron or to lose electron. And therefore these elements are zero valent, and they exist as monoatomic gases, that is chemical inertness in other words. But if we consider xenon, then xenon has a larger atomic size and lower ionization enthalpy compared to helium, neon, argon and krypton. Just go through the position of xenon. Xenon is quite at the bottom of the group. So it has little larger atomic size and lower IP compared with the earlier noble gases, that is helium, neon, argon, krypton, and therefore xenon exhibits higher oxidation states. Its outermost shell has d orbitals. The paired electrons of the valence shell can be unpaired and promoted to the empty d orbitals. And these unpaired electrons are shared with fluorine or oxygen atoms. And therefore, covalent compounds showing higher oxidation state are formed. Some of the examples are given: xenon difluoride, xenon tetrafluoride, xenon hexafluoride. In bracket, oxidation state of xenon is shown. So xenon exhibits higher oxidation state. But this is possible only with fluorine and oxygen. Now reactivity towards hydrogen, chemically inert. Then reactivity towards oxygen, again chemically inert. And reactivity towards halogen, only krypton and xenon directly react with fluorine to give fluorides. So as we saw, xenon fluorides. And reactivity towards metal do not directly react with the metals. Now let us consider xenon fluorides preparation. Xenon fluorides are prepared by direct reaction of xenon and fluorine in different proportions and conditions, such as temperature, electric discharge and photochemical reaction. So here is the preparation of xenon difluoride, xenon tetrafluoride and xenon hexafluoride. So Xe plus F2 sealed nickel tube 400 degrees centigrade, it produces xenon difluoride. Then Xe plus 2F2 minus 80 degrees centigrade electric discharge, it produces xenon tetrafluoride, which can also be prepared by another way, 5 to 6 atmospheric pressure, 400 degrees centigrade, nickel tube, 1:5 proportion of xenon and fluorine. It also produces xenon tetrafluoride. And xenon plus 3F2 electric discharge, low temperature gives xenon hexafluoride. Some of the reactions of xenon difluoride. First is hydrolysis. Xenon difluoride undergoes hydrolysis to form hydrogen fluoride. So 2XeF2 plus 2H2O gives 4HF plus 2Xe plus O2. Second reaction is with phosphorus pentafluoride. Xenon difluoride forms an adduct on reaction with PF5. Adduct means addition product. So XeF2 plus PF5 gives XeF2PF5 addition product. Then xenon trioxide. Fluorides of xenon react with water to form xenon trioxide. This can be considered as hydrolysis. So 3XeF4 plus 6H2O gives 2Xe plus XeO3. XeO3 is your xenon trioxide plus 12HF plus 1.5 O2. And XeF6 plus 3H2O gives XeO3 plus 6HF. Oxyfluorides of xenon. So these are 4 oxyfluorides of xenon exist. First is XeOF2, xenon oxydifluoride. Then XeO2F2, it is xenon dioxydifluoride. Then XeO3F2, xenon trioxydifluoride. And XeO2F4, xenon dioxytetrafluoride. So these are some of the oxyfluorides of xenon which exist. Then preparation of xenon oxyfluorides. First, partial hydrolysis of xenon fluorides produces different oxyfluorides. So XeF4 plus H2O at 80 degrees centigrade it forms XeOF2 xenon oxydifluoride plus 2HF. But without heating it produces xenon oxytetrafluoride. So second equation is XeF6 xenon hexafluoride is taken now. XeF6 plus H2O gives XeOF4 plus 2HF. Reaction of xenon oxytetrafluoride with silica or hydrolysis produces xenon dioxydifluoride. So 2XeOF4 plus SiO2 gives 2XeO2F2 plus SiF4 and XeOF4 plus H2O gives XeO2F2 plus 2HF. So these are the structures of some of the xenon compounds. Xenon difluoride is linear. Xenon tetrafluoride is square planar. Xenon hexafluoride is distorted octahedral. Then xenon trioxide is trigonal pyramidal. And xenon oxytetrafluoride is square pyramidal. Now uses of these noble gases are quite important. So uses of helium. Mixture of helium and oxygen is used for the respiration by sea divers. It is also used for artificial breathing of asthma patients. Mixture of helium and hydrogen is used for filling balloons. It is used in producing inert atmosphere in metallurgical processes and welding of metals. It is used to produce and sustain powerful superconducting magnets which are used in NMR spectrometers and magnetic resonance imaging, that is MRI systems for clinical diagnosis. It is used as shielding gas for arc welding. It is also used in gas-cooled nuclear reactors. So all these are uses of helium. Liquid helium is used for producing low temperatures required for research. Then it is used in supersonic wind tunnels. Then it is used in low temperature gas thermometry for production of lasers. It is used to pressurize fuel tanks of liquid fueled rockets. A helium nucleus is used as a bombarding particle for disintegration of atoms. So, in various fields, this helium gas is quite important, or it has a very wide use applications. Let's proceed with the uses of neon. It is used in neon discharge lamps and signs. These signs are visible from long distance and also in mist and fog. We always found these neon signs. Then mixture of neon and helium is used in certain protective electrical devices such as voltage stabilizers and current rectifiers. It is used for production of lasers and it is used in fluorescent tubes. Then uses of argon. It is used for producing inert atmosphere in welding and steel production. Mixture of 85% argon and 15% nitrogen is filled in electric bulb to increase life of the filament. Then argon is used in filling fluorescent tubes and radio bulbs. It is mixed with neon to get light of various colors. So these are some of the uses of argon. So students, in this class, we discussed group 18 elements, that is noble gases. This is how we completed the discussion of chapter number 7, that is elements of group 16, 17 and 18 elements. Thank you.